Welcome back to the Deep Dive. We're the place you come to get the real story behind the sources, breaking down the data, and, well, bringing some clarity to things that really affect us all. And today, we're looking at something so fundamental, so every day, you almost don't think about the science behind it. I mean, that feeling, right? When the sun comes out, that warmth on your skin. Could be just a nice, gentle touch on a cool morning or, that intense heat in the middle of summer. We all know it. We know the sun feels hot. Or maybe more accurately, it makes things feel hot. But have you ever stopped and really wondered why? Like scientifically, what's going on? Why does the sun feel hot? It sounds simple, almost like a kid's question, but wow, the science behind it. It pulls together physics, astronomy. It's fascinating. So today, that's our deep dive. We're tracing that energy right from the sun all the way to your skin, giving you that shortcut to really understanding something you experience basically every day.
Yeah, it's a great question because it really does connect us to some really basic principles, energy transfer, thermodynamics, stuff that, makes the universe tick. So our mission today, if you like, is to follow that energy's journey from inside the sun, across all that space, right down to Earth, and then boom, it becomes heat. We're going beyond just the sun is hot. We want to explore the how and the why. We'll break down the tricky bits into stuff that hopefully makes you go, aha, okay, now I get it when you're out in the sun next time.
Okay, let's start right at the source then, the sun. Our sources often describe it, pretty simply, an enormous fiery ball of gas burning incredibly hot. But fiery and burning might give the wrong impression, right? It's not like a log fire.
Exactly. It's not combustion in the way we usually think of it.
Correct.
Well, it's a giant nuclear reactor, essentially. Deep inside the core, the pressure and temperature are just unimaginable, over 15 million degrees Celsius.
Wow.
And under that pressure, hydrogen atoms are forced together so violently they fuse, becoming helium. That's nuclear fusion.
Right, Einstein's EBC stock thing. Tiny bit of mass, huge amount of energy.
Precisely. And the sun is just mind-bogglingly massive. It's got like 99.8% of all the stuff in the whole solar system.
You could fit over 1 million Earths inside it, I read somewhere.
Yeah, something like that. And all that mass creates the gravity that keeps the fusion going. It's this continuous, controlled explosion, releasing just immense amounts of energy.
Which then has to get out of the sun somehow.
Right, works its way through the sun's layers. But the key point is this constant energy production. And it makes you think, doesn't it? How can something so far away, what is it, 150 million kilometers?
About that, yeah. 93 million miles.
How can it affect us so directly every single second?
So how does it send that energy across all that distance? It's not like there's air carrying the heat.
No, exactly. Space is mostly empty, a vacuum. So it can't use conduction, like heat traveling up a metal spoon, or convection, like hot air rising. Instead, the sources are clear. The sun blasts out massive amounts of energy in all directions, mainly as electromagnetic radiation.
Electromagnetic radiation. Okay, like light.
Like light, yes, but visible light is only a tiny part of it. Think of it as energy traveling in waves, or maybe packets of energy called photons. These aren't like sound waves needing air or water waves. They're electromagnetic waves. That includes everything from radio waves, microwaves, infrared.
The visible light we see.
Then ultraviolet, X-rays, gamma rays, the whole spectrum.
Okay, so it's sending out this whole range of energy waves.
Yeah.
But which part makes us feel warm?
Good question. The crucial part for that feeling of warmth is that this energy includes both light and heat. Now, technically, the waves themselves aren't hot. They carry energy.
Right.
Visible light lets us see, obviously, but it's mainly the infrared part of the spectrum invisible to our eyes, but very much there, that carries a lot of the energy that gets converted into heat when it hits something.
So the sun is like a giant lamp and a giant radiator.
Yeah, that's a pretty good way to put it. It's delivering energy in these, well, invisible packages, these photons. And because space is a vacuum, that energy travels pretty much uninterrupted. It doesn't lose much on the way.
Until it hits something, like Earth.
Exactly, until it encounters matter. And it's a constant stream pouring out in all directions, all the time.
That journey, it's incredible. These energy waves, these photons, crossing 150 million kilometers of empty space.
And they do it fast.
Yeah, speed of light, right. About 300,000 kilometers per second.
Which means the sunlight hitting your face right now actually left the sun. What, about 8 minutes and 20 seconds ago?
Just amazing. 8 minutes ago, it was part of the sun. Now it's here warming my hand.
And think about space itself. It's incredibly cold out there, even though all this energy is constantly streaming through it.
Right, because there's nothing, or almost nothing, to absorb the energy and get hot. No medium for conduction or convection.
Precisely. The energy just passes through.
So it's this relentless shower of energy constantly bathing our planet. Invisible, powerful.
Yep, a continuous flow.
So, okay, the energy makes the epic journey. It arrives.
Yeah.
What happens then? That first contact moment when the waves hit Earth, how does that turn into warmth?
Right, this is the crucial moment of interaction. The transformation starts here. When these electromagnetic waves reach Earth, they hit, well, basically everything.
Everything.
Pretty much everything in their path. The sources list examples. Your skin, the sidewalk, the grass in the park, your colorful toys, even the clothes you're wearing, the ground, the air, the water.
Okay, so they hit stuff, then what?
Then the really important step. When this energy touches these things, it gets absorbed.
Absorbed, okay.
Yeah.
So the material kind of takes the energy in.
Exactly. It's not just bouncing off, although some reflection happens too, which we'll get to. But a lot of the energy is absorbed by the atoms and molecules of the material it hits.
How does that work, the absorption?
Well, think of a photon, a packet of energy hitting an atom. The atom can absorb that photon's energy. This bumps an electron inside the atom up to a higher energy level. It gets excited, basically.
Okay, excited atoms.
But that excited state usually isn't stable. The electron wants to return to its normal, lower energy level. To do that, it has to release the extra energy it absorbed.
Ah, okay. And that released energy, is that the heat?
A big part of it, yes. A significant chunk of that released energy makes the atom itself and its neighbors vibrate or move around more energetically. Faster vibrations, faster movement.
And that faster vibration, that is heat.
That's essentially what heat or thermal energy is at a microscopic level. The kinetic energy, the motion of the particles in a substance, the more they jiggle and bounce around, the higher the temperature.
So the sunlight isn't hot as it travels, but the energy it carries becomes heat when something absorbs it and starts jiggling.
You've got it. The wave itself is energy. The absorption converts it into the particle motion we perceive as heat. It's an energy transformation.
That's a really key distinction. Energy carrier becomes particle motion, becomes heat. Okay, so once that sunlight energy gets absorbed, the object starts converting it into this thermal energy, this heat.
That's right.
The sources use a nice analogy. It's just like when you run really fast or play a lot of games, your body starts to warm up, right?
Yeah, that's a good way to think about it biologically.
You're using chemical energy from your food to move your muscles, but it's not 100% efficient. Some of that energy conversion results in heat. Your body literally gets warmer because of the energy being used.
Metabolic processes generate heat.
And the sources say the same thing happens with sunlight. The energy arrives, gets absorbed, and is transformed into heat, making the absorbing object warmer.
Exactly the same principle. First law of thermodynamics in action. Energy changes form. Light energy becomes thermal energy.
So let's just nail this down. The sun isn't like beaming heat rays at us directly like a space heater.
Not in the sense of sending hot particles or heating the space between. It's sending electromagnetic energy.
Infrared, visible light, some UV.
Right. And our bodies, or the ground, or whatever, absorb that energy package. Then we do the conversion. The object itself turns that absorbed energy into the random motion of its own particles.
Which is why an astronaut in space, even in direct sunlight, doesn't instantly cook, right? Their suit might absorb some energy and get warm, but the space around them stays cold because there's nothing to absorb the energy.
Precisely. No absorption, no conversion, no heat felt in the surroundings. The absorption by matter is the absolute key step.
Okay, so the more energy something absorbs, the hotter it gets. Makes sense.
Yes, there's a direct relationship. More photons absorbed means more energy converted, means faster particle vibration, means higher temperature.
But as we know, not everything heats up the same amount, even in the same sun.
Ah, yes. That's where the properties of the material itself come into play. Things like specific heat capacity.
Specific heat. What's that again?
It's basically how much energy you need to add to raise the temperature of a certain amount of a substance by 1 degree. Water, for example, has a very high specific heat capacity.
I mean, it takes a lot of energy to warm water up.
Exactly. Compared to, say, sand or rock. Land heats up much faster than the ocean when the sun hits it, even though they're absorbing solar energy.
And cools down faster at night, too.
Yeah.
That drives sea breezes and stuff, right?
Absolutely. It's fundamental to local weather patterns and even global climate dynamics. How different surfaces absorb, convert, and then hold onto heat is crucial.
So this whole process, the sun sending energy, Earth absorbing it, converting it to heat, this isn't just about feeling warm. It's literally what keeps the planet, well, livable.
Fundamentally, yes. This constant energy input from the sun and the way our planet's systems, atmosphere, oceans, land absorb and redistribute that energy as heat, that's what maintains Earth's overall temperature balance.
A balance that allows for liquid water, which is kind of important for life.
Kind of essential. Without this solar energy absorption and conversion keeping things within a certain temperature range, Earth would be, either a giant snowball or scorched rock. This process makes our planet habitable.
Which brings us perfectly to that other thing we all notice. Why some things get scorching hot in the sun, while others stay relatively cool. Like you said, think about walking barefoot on a summer day. You feel it instantly. Dark asphalt.
Oh.
Ouch.
Yeah.
Metal slide. Forget about it.
Definitely. You learn quickly.
But then you step onto the grass or maybe some light-colored pavement, and it's relief. Same sun, totally different feeling.
And that difference comes down mostly to two things. How much energy is absorbed versus how much is reflected.
Okay, so it's not just absorption, but also reflection.
Right. Our sources put it clearly. Darker colors and certain materials are much better at absorbing the sun's energy.
Why dark colors?
It's about the pigments and the molecular structure. Dark objects absorb more wavelengths of light across the visible spectrum and often more infrared, too. They basically trap more of those incoming photons.
Soaking up the energy, like a sponge, as you said.
Pretty much. And because they absorb more energy, they convert more energy into heat, so they get hotter.
And lighter colors.
They do the opposite. Lighter colors reflect more of the sunlight away. They bounce a larger fraction of those photons back off the surface.
So less energy gets absorbed.
Surplus energy gets converted into heat, and the object stays cooler. It's a simple but powerful effect.
The sources give classic examples. A dark-colored sidewalk or a black car will get much, much hotter.
Oh, yeah. You can fry an egg on a black dashboard sometimes.
Than a light-colored t-shirt or a patch of green grass.
Exactly. White t-shirt reflects most of the visible light. Green grass reflects green light, which is why it looks green, and uses other wavelengths for photosynthesis. Plus, water evaporating from it cools it down to transpiration.
So it's a combination of color, material properties, and sometimes even biological processes like with the grass.
It all plays a part. But the core idea is absorption versus reflection. Dark absorbs more, light reflects more.
And this isn't just trivial stuff, is it? Like architects think about this for buildings.
Absolutely. Reflective roofing materials can significantly reduce cooling costs in hot climates. Urban planners worry about the urban heat island effect, where cities full of dark asphalt and concrete get much hotter than surrounding rural areas.
Because all those dark surfaces are just soaking up the sun's energy and radiating it back as heat.
Precisely. So even choosing light-colored clothing in summer isn't just about fashion, it's applied physics, helping you stay cool.
It really is amazing when you piece it all together. The sun, so far away, sending energy
Just constant.
across space just via these invisible ways. And that energy becomes the light and warmth that are just essential.
Utterly essential. That warmth is fundamental for life as we know it.
The sources mention key things, helping plants grow and keeping our planet cozy.
And those are huge. Photosynthesis driven by sunlight is the foundation of almost all food webs on Earth. Plants capture that solar energy, turn it into chemical energy food, basically.
So we're literally eating sunshine, in a way.
In a very real sense, yes.
Yeah.
And keeping our planet cozy, that's about maintaining the temperature range where water can be liquid.
The Goldilocks zone stuff. Not too hot, not too cold.
Exactly. Liquid water is crucial for the chemistry of life. Solar energy also drives the water cycle evaporation, clouds, rain.
And weather patterns, wind, ocean currents.
All driven largely by the uneven heating of the Earth's surface by the sun. Temperature differences create pressure differences, which drive air and water movement, distributing heat around the globe.
So it's not just warmth, it's the engine driving Earth's entire climate system and making complex ecosystems possible.
Absolutely. Connecting it back to that bigger picture, the sun's consistent energy output puts Earth in that habitable zone, making liquid water possible on the surface. That's the baseline.
Without that warmth, it's just ice or steam.
Pretty much. And liquid water is the solvent, the medium where all the complex chemistry of life happens. And it goes beyond just surface temperature. Solar energy drives geological processes too, like weathering. It influences atmospheric composition over long timescales. It powers all these intricate feedback loops that help keep our climate relatively stable, at least stable enough for life to have evolved over billions of years.
So keeping our planet cozy is this incredibly complex balancing act.
It really is. It's about absorbing the right amount of energy, converting it, circulating it, and eventually radiating the excess back into space to maintain a dynamic equilibrium.
If that balance gets thrown off.
Then you see climate change, potentially drastic shifts. The amount of energy coming in is fairly constant, but how we absorb, reflect, and trap that energy here on Earth can change.
So without that constant, precisely tuned energy delivery from the sun and Earth systems processing it, we'd be a dead rock.
A frozen or incinerated dead rock, yes. The sun's energy and how Earth interacts with it is truly the foundation of everything that makes this planet alive.
Okay, let's wrap this up. It's been quite a journey from the sun's core to our skin. It starts with that incredible nuclear fusion furnace deep inside the sun.
Yeah, turning mass into pure energy.
That energy travels 150 million kilometers as electromagnetic waves, light, infrared, the whole spectrum. Invisible energy packets called photons.
Traveling at the speed of light through the cold vacuum of space.
Then they arrive at Earth and hit, well, everything. Our skin, the pavement, leaves.
And the key step happens. Absorption. The material takes in the photon's energy.
And then comes the conversion. That absorbed energy makes the atoms and molecules in the object vibrate faster.
Which is thermal energy. That's what we feel as heat.
So it's not heat rays, it's energy waves that cause us to generate heat upon absorption.
Crucial distinction.
And the reason dark things get hotter.
They absorb more of those energy waves, converting more into heat. Lighter things reflect more away, absorbing less, staying cooler.
So next time you're out feeling that lovely sunshine, remember that whole chain reaction. Energy from a distant star traveling across space, being absorbed and transformed into the warmth that makes life possible here.
It's quite a thought.
What an amazing star we have. Seriously powerful.
It truly is. And, thinking about this energy transformation, sunlight into heat, it makes you wonder. Well, this principle, energy changing forms, it's everywhere, right? Not just with sunlight.
Like the heat from running you mentioned earlier.
Exactly. Or think about your phone getting warm when you use it a lot.
Yeah.
That's electrical energy converting partly into heat. Or a light bulb electricity into light and heat.
Yeah, true. Even friction generates heat rubbing your hands together. Kinetic energy to thermal energy.
Right. So here's a thought to leave you with. Beyond the sun, what other everyday things you barely notice, are actually demonstrations of these fundamental energy conversions happening right under our noses? What other hidden energy transformations are shaping your experience?
That's a good one. Makes you look at things a bit differently.
Hopefully. Keep noticing. Keep asking why. That's what science is all about. We hope you enjoyed this deep dive, and we'll catch you on the next one.
Until then, stay curious.
Don't forget to like and subscribe.